All right. Good morning, everyone. First of all, thanks for your time and especially to the committee members. I had really short notice to let them know about the different state. Thanks for your time, sir. So, as the topic states, it's distributed spectrum coordination schemes for coexistence of multi-radio platforms. I won't be keeping you tight for a long time. It's going to be 30 odd slides, and I'll try to keep it pretty straight and simple. And the purpose is to highlight our work and also get your sincere feedback for the topic. Alright, so the work is on multi-radio platforms. By multi-radio platforms, what you mean is simple cell phones and all those laptops with multiple radios. Wi-Fi, Bluetooth, WiMAX, GPRS, all of them are now getting embedded on small devices. So some issues faced by those devices and how to address them, that's the whole objective of this research work. So let's actually get into the topic. So the outline of today's presentation is going to be the overview, starting with the motivation behind the work and the methodology that we followed. And going into it, I'll detail the experimental setup, the specifics of the experiments, and we'll first study what is the performance degradation when there is no coordination also. And then we'll talk about what are the existing solutions, highlight what is the proposed solution from our side, and finally we'll talk about the performance with the coordination. What gains do we see by applying our coordination schemes? Let's get into it. Alright, so motivation for this work is with the growing number of small form factor devices like cell phones and laptops with 5 to 6 radios, you have scenarios wherein these devices are put together in very small environments like small offices or conference rooms. The picture on the right bottom corner, you see a representative sample of a home office wherein you have around 20 different devices with multiple radios. And what could be so what we think is there is a lot of situations wherein you have interference between these multiple radios and due to like co-channel and adjacent channel interferences. So the purpose is to first classify the interference wherein it is due to intranode and internode. Intranode interference is the one wherein the radios are placed in the same platform and you have interference because of in-platform interference. And there is internode, which is due to the proximity wherein radios or devices are located in, basically you see interference from adjacent platforms. And the two questions that we want to answer is how significant is internode interference? Why particularly internode? Because it is more easy to attack the intranode problem because the manufacturer is the one who is placing these radios and he has ways to address it. But in the case of internode, you have like a IBM laptop sitting besides very close to an Apple laptop, and there are situations which we need to address. And the second question is, can we address both the interference situations using a common distributed coordination scheme? So the methodology is pretty simple. You choose a set of radio technologies, throw them in a dense scenario on a 1-to-1 scale, like say you choose 20 odd radios and put them in orbit and try to operate them with realistic workloads, say for example the web browsing for Wi-Fi and audio sessions for Bluetooth, and try to evaluate the degradation and devise your scheme and try to see the gains in that setup. So the specifics of the experiment specifics for the work basically starts with we actually ended up trying to analyze dual radio setups wherein we wanted to test Wi-Fi and Bluetooth to start with instead of taking all the radios. So this is the two radios which we focus on, and the traffic scheme that we operated on them are like for Wi-Fi we wanted to represent the web browsing. We did TCP file transfer and UDP multiple random sessions and also Bluetooth voice sessions. And the experiment duration was, each experiment was like for 1 minute wherein you create such scenarios of multiple radio operating simultaneously together. And the things to take from this slide are the power of transmit power for Bluetooth. We use class 2 predominantly, which is more prevalent in the existing real world setups, which are basically low power Bluetooth dongles. And the other thing is we use both auto rate enabled, basically the 5 rate case, wherein we use both auto rate enabled Wi-Fi and auto rate enabled Wi-Fi and also fixed rate at 36 Mbps. So
is it sort of straight off out of the book 72 channel hopping, or is it the reduced hopping when it sees that there's an 802.11? Because there isn't the standard
Right.
a reduced like
It's
50 hop
Mm-hmm.
version.
No, this is
50
not.
channel
This is
hop.
like the basic version, the first version which had full hopping. And these are like the Bluetooth dongle that is used is the Belkin's first version of USB dongle that they released. So what we did was we wanted to choose some representative samples, and we tried to emulate on different topologies. Some of them denser and some of them really spaced apart. And the first topology that you see has both internode and intranode. This is a topology wherein you have on the same device you have both Bluetooth and Wi-Fi. And the other cases we wanted to study predominantly the internode effect, wherein there are no multiple radios in the same device. So what is the thing first to observe is without coordination, what are the effects on the performance? So such experiments we were able to leverage. You have the different Wi-Fi loads, and in here you see again there is a drop in Wi-Fi naturally to boost. Drop in Bluetooth naturally to boost Wi-Fi gains. And
So-
this is
So have you accounted here for the coordination channel?
yes
The overhead?
the overhead. Yes,
So what is the size of this coordination?
coordination overhead is it's not even 0.2% for 16 radio pairs, wherein the total because we exchange only 16 bytes of information.
So what
per
are you
se-
exchanging on this coordination channel?
Yes, we basically exchange the session on time, the time it turns on, and the session duration. So basically, it's totally 16 bytes per second. We actually do it through Ethernet here and out there. So that could be thought of. I don't take into consideration the Ethernet overhead. So what I'm saying is just the
frequency.
See, the question is this, right? You said this whole study is based on, if you sort of throw in a lot of radio, like multi-radio platform, lots of them, in a very dense scenario.
Yes.
The fundamental question that sort of needs to be thought of is, if you now have some kind of a channel where you're going to coordinate this, at what point does basically it sort of gets to the point where there are no returns anymore? Right? When you think about this, right? At some point there is so much of overhead that's being exchanged.
Mm-hmm.
I mean, you sort
But
of
you don't-
assume that a lot of things were known. You said, oh, we knew where they were, we knew what kind of channels they. But really,
No, they are actually exchanged. In here too, we actually exchange the location.
so there has to be some way of sort of understanding at what point is this going to sort of fall apart, or does it never fall apart?
Right. In our cases, what we try to, in order just to address that question, what we did was we used again similar multi-dense radio, and what we did was we found out what is the total amount of information that we need to exchange per second, and that is like we just exchange 16 bytes of information in order to achieve whatever all the three coordination case, and only when that number increases, when the amount of information that we exchange increases, there could be like a chance wherein it could fall apart. But
You have a periodic refresh of
Yes.
this information, right? So what was the frequency that you used for these results?
for these users, we do only per second. Like every
One per
second,
second.
yeah, one per
But you
second.
also have to explain that overhead in this case would be linear, not
Yes,
Right, that's what I sort of want to understand.
there is a slide later on.
Which says what is the overhead for.
What is the
But
overhead
that's with the assumption that only local information is relevant and that you have relatively large coverage.
Yeah, we assume that control radio has like it completely covers the region of operation.
Right, because sort of fundamentally, if you look at it, right, you can ask this question of any communication system where there is some stuff that you need to infer,
Hmm.
and you need to ask the question of how much overhead
Do they
has to
have?
go into understanding it. And what will happen is that usually when the scale or the dimension of these things grow, at some point you will hit sort of a floor, right, where
Right. What we did
So
was
the
we
question-
increased that K to like 32 Ks, and we tried to find out what is the overhead that we see in this. So we'll actually see.
Yeah, I think that's generally true. I think here the idea is that session level information is sufficient, which is not like bit level or packet level. And that's all you're doing is adjusting the session state.
so you're just basically controlling the application. That's all.
Right.
That's the thing which actually gives us the advantage. Instead of going at the packet level. Sure.
So what is offered and what is session throughput?
So session throughput is at per Wi-Fi receiver, whatever is whatever is being when I transmit from one transmitter to the receiver, right? So what is the achieved throughput for say a UDP session?
So
Achieve.
what is the application rate?
Yeah, offered is the total application.
And the total offered in the system.
Total offered load in the system. Sorry. So okay, from here on the curves will be for only internode case, wherein we'll test all the 4 schemes: Bluetooth backoff, 8-adapt, and SIFET. And what you see in this is on the right top you have a normalized result with respect to no interference case. So when you have say no coordination having 50% Wi-Fi and 60% Bluetooth, what it means is it is like 60% with respect to no interference case when there is no inter-radio operation. So in all the 3 cases, what we see is Bluetooth backoff naturally as expected, getting a hit on Bluetooth while Wi-Fi being improved to around 80 to 90% in like all the topologies that we see going down. And we see a common trend wherein the purpose is to make sure the total network throughput is maintained constant or increases downline with more coordination schemes, better coordination schemes. At the same time, we also want to make sure that Bluetooth is not compromised way beyond than it is necessary. Like in backup, we had this more than minus 40, like the degradation was more than 40%. And in rated app, it was better because it was having some kind of channel utilization even when it was interfering with Wi-Fi. And the SARBT was more appropriate when compared to the Bluetooth rate because you don't compromise Bluetooth unnecessarily. So the trend is generally over different schemes, the total network throughput is constant or growing, and Bluetooth degradation is decreasing over each in all the 4 different topologies that we saw.
What is the yellow bar?
Yellow is the total network throughput. That is basically a sum total of Wi-Fi and the Wi-Fi throughput in absolute numbers and added to Bluetooth. So again, the drop could be at different levels, but we see a similar trend for in the case of both topology 2, 3, and 4 and 5. I mean, this common thing to take from each slide is there is scope for better scheme, and SIRBT achieves a better balance between the two. Topology 4 again, you have a similar case when Bluetooth degradation reduces from 50% back to 25%, and there's a little compromise. So what we want to achieve is a balance between the two and try to gain a better overall throughput. And the same thing we did with TCP case, wherein we did a basic file transfer between these Wi-Fi links, and what we basically measured was the amount of time it took to transmit one MB file, and correspondingly we also see the Bluetooth throughput on the right hand side, the blue curve. So what we see is in here Bluetooth backoff, we turn on both Wi-Fi and Bluetooth at the same time. So naturally when it backs off, Bluetooth is completely suppressed, and Wi-Fi, the time to transmit is almost close to the no interference case. I mean, I'm comparing the third curve with the first curve. So again, in the case of rated app and SIRBT, we let Bluetooth achieve some throughput. We see there is phenomenal decrease in also the time to transmit. There is improvement in time to transmit when compared to the no interference case, which was around 35 to 38 seconds. Right. And we did the same experiment with VLC client. VLC is UDP video stream. We see both losses in both cases because Bluetooth is still operating, interfering with Wi-Fi. But with coordination it is better when compared to the The point to take in this case is the video is again does not have any feedback or RTP mechanism to explain And so the objective is to again try to balance the radio types A and B, and also provide a generic solution which is not tied to one particular. So as we wanted to also see what is the price that we pay for in terms of control overhead that happened. So as of now, since it's just an application level adaptation, there is your control information need not be exchanged at your control information basically is exchanged at very low rate. It is only exchanged like 1 per second, and what we have is like 11 byte static packet size and also 16 byte radio 16 byte packet size, which depends on the number of radios. So if you have two radios, Wi-Fi and Bluetooth, you have like 32 bytes, and if you have radio n radios, then you have 16 into n bytes for going into radio type. So it basically what we wanted to study was with increased number of radio nodes, where k increases from 8, 16, and we did with 22 max, and basically it's pure calculation of amount of bytes that is required and the total control data per second in bits per second compared to the overall gain that is achieved through coordination, and the overhead is roughly only 0.1% for even 20 node case. So the advantage is because we only do application level adaptation. And so this really says it's pretty acceptable system design, and there is we don't see an immediate bound for the control in our case. So in conclusion, what we have done is we have investigated the interference effects in one-on-one real world case. We designed and tried to evaluate the radio independent solutions, basically with Bluetooth backoff, rate adapting SARBT scheme, and each giving pretty comparable results when compared to SARB. For example, in Bluetooth backoff, you get around 30 to 100% gain in Wi-Fi, but Bluetooth is compromised. Again, rate adapt achieves a balance. The degradation is only 20%, while Wi-Fi gains around 50%. And SARBT achieves a better balance, improving it basically gets more than 15 or 20% when compared to the previous games. So what we have is not just these numbers. The importance is we have a scalable test platform wherein you can test any scenario. 1, 2, you can emulate, basically put in any number of radio types instead of just Wi-Fi and Bluetooth. You can in future put in radio type A, B, C, and try to simulate such a scenario and study the effect on each case. And the future scope is, as you have the platform, you can always. We wanted to actually work on this, but we didn't really get a chance to do that. What we thought of was a QoS based priority service rate adapt, wherein say a particular link demanding a particular QoS performance, say for example a particular latency or a throughput, and then the other radios cooperatively with each other to make sure that it gets. And similarly, the SARBT scheme, instead of doing with theoretical numbers, we could again improve it using actual RSSI values from the control channel, and also try to have feedback from the actual self throughput, and also do symmetric all radio adapt. That will be like the best case in the case of coordination.
So in the case of QoS space, you will have to set more control.
Yes. Now what is exchanged is the minimum QoS rate alone. Like what is the minimum rate that I want? Like the Bluetooth exchanges 64 kbps as the rate. In future, yeah, if you want, there should be two more octets. One for the QoS type and the other for QoS value that you want.
It's also now it's can be at 1 second.
Second, I think what algorithm is more complicated. Solve that.
But if you want to adapt all the radios to the QoS requirements.
So you're doing it as a kind of session time constraint. So session starts for minutes or hours. So okay. So
The sessions for wireless devices, once they last on
So if you are here, do it half a second, but this is still session level can be very information. I think the algorithm is not obvious because it requires quite a bit of and estimated some trade-offs. And I think ultimately the symmetric adaptation will be quite. But the point here is everything is done at the traffic shaping level with session, and it seems to at least give you a fair approach to your system without catching it.
these radios were getting those rates, they have to somehow keep that information that I'm happy.
Well, who will be happy with that? It's an autonomous system, right? It's a local decision that you make based on your neighbors. You can put, actually, your own radio can put a more aggressive policy. This is also based on some common policy that people put friendly policies or Intel-shaped software into friendly policy. So that part is relatively recently on. This is a socially friendly like TCP, which I feel very much like a local TCP backwards. But TCP alone didn't do the job.
As I said, the complexity improves greater when you think of QoS-based scheme in terms of coordination scheme, but not at the level
Again, the
of.
feedback adaptation along with the CSCC, if you distribute the information over the RSSI and interference with the each node, they can do a distributed algorithm, do something closer to the kind of thing getting closer to the optimal scheduling.
When you do this session level information exchange, again there is a lot of open research issues which open up. One, to start with the bullet point at the bottom, you have this lot of security issues when you exchange CSS information. What data needs to be exchanged, and why should radios cooperate with each other? Why should Bluetooth compromise when compared to Wi-Fi? So those are things which need to be addressed. And one other thing that we think of going down the line, when you have multiple such radios and each device is having multiple such radios, we are thinking of, and also with the information that you have, you exactly are aware of the topology. Why not we do multi-radio hopping, like multi-radio data forwarding, instead of, say for example, I transmitting my data through Wi-Fi to a receiver B. Instead, I could take a route through Bluetooth to receiver C, and then, to a different guy C, and then he doing it through Wi-Fi. So basically, we are thinking of having a futuristic thing wherein you will have multi-radio, multi-hop forward with this scheme in place and with all the additions that we think of. And that pretty much summarizes all the work. First of all, very big special thanks to my senior Xiangpeng and Masood. Xiangpeng is not available, he's with SUNY California. He's the one who actually has built the CSCC platform, without which no coordination is possible. And Ivan Sisker and the whole Orbit team. 90% of my work has been in Orbit. There is no simulation whatsoever in this case. And for that, they have really provided a very stable and dependable environment in Orbit. And I should also apologize for all the Orbit hogging that I did in the whole process. I was almost like hogging every 2 hours every day for the whole, almost for 4 months. So, and Ivan has always been complaining to me about that. Okay, and that's it for presentation. I'm open to your feedback.
So do you have any comments about how this approach to dealing with coexistence would compare with the adaptive frequency hopping that Bluetooth, the second version of Bluetooth
Right.
proposes?
By comparison, what I think is in the case of adaptive frequency hopping, when the density increases, when more number of radios come in picture. Now in this case, we haven't yet even simulated a scenario wherein you have multiple access points. Like you have one guy operating in channel 6 and the other in channel 1. All we do is all the Wi-Fi is operating in single channel. So the very fundamental thing, that is availability of free channels, could be a question when you have more number of radios. There could not be available frequency channels to hop around. So the fundamental of AFH, the dynamic frequency hopping itself could fail when you have lesser and lesser available frequencies to hop. So that's why we think going down the line, when you have more and more radios coming in and more radios operating like very close channels in the same frequency or in the analyzing band, your adaptive frequency hopping and the transmit power control might not really work, and you might not have that leverage to adapt. Being session level, you have the whole constraint is what kind of application you are running. Do you have the leverage to wait for 1 second to do basically these series?
on orbit. You guys need me. We'll take care of it later.
So do you have any comment on the viewers topic that remains open?
Well, I mean, we still don't know what QoS is. I mean, it really depends on who we are talking to. I mean, once you talk to the guys that are working on packet level stuff, they start talking about, into packet and scheduling stuff that's happening in that layer. And, when you talk to some other, more executive kind of guys, they started talking about user perceived,
Right.
quality and all
So I
that.
had a question, you showed like a video and you said both are looking back. So I'm saying like, so what is the point of this? Right?
No.
So there has to be some, that's right, when you sort of control something in the application, and I think he was also asking some questions about
What is?
there has to be some notion of, I mean, it's sort of a fuzzy metric, I think, but still.
There is very standard metric.
If there is a subjective.
Yeah, but I don't think that's,
No, it's not.
right, that's what I was asking, right? I mean, where there is some notion of a metric, and then you can sort of say, okay,
Metric acquisition, he was supposed to do that here, next person.
Still do it.
The way to do it is to RTP feedback.
Yeah.
That automatically lowers the rate to assessment.
But what you can obviously do is put these videos to subjective quality testing and get those numbers.
Yeah, but you would not watch that either way.
Yeah.
see, the thing is that we're trying to sort of do some kind of a spectrum coordination and provide some kind of guarantees, right? I mean, you have to sort of have these predefined. So, and say like, okay, this is what, and again, you can show the value to different people, right? Some people, it depends on sort of the quality of life in some sense. Like people who have sort of lousy connections all the time will say, okay, this is so bad.
I think in this time, fully different cases unwatchable. But what happens is if you put RTP rate feedback, you'll settle down at a lower quality, lower rate each case. And in one case it might be 100 kilobit, in another case it might be 100. That is your number. But doing hard QoS guarantees, I don't think can be a real objective because
No, yeah, I mean, no, you're right, it can't be hard, but I'm saying you could use other layers that you have not, exploited right now.
I think
That's what.
this topic is limited to this layer, but the 5 layer and 9 layer are different.
Final math layer, I mean, I think you need to go to more higher than I think that overhead issue would be a lot.
So
Like,
that's
you
why
get most of
this
the gains here by.
This is kind of like a micro internet kind of approach. So it's okay, we conducting by TCP cases, with most of it obviously doesn't do very well for people.
What I'm saying, the returns you get, I think, at least 60% of the returns from doing the session level.
But I can also see that tighter mechanisms below.
I think that will be only fine tuning.
So your intuition is that this kind of
Because I mean, he said that localization actually that is a big problem. Right? He says that he assumes localized patient information. He's hiding a big thing under the carpet there. And maybe the propagation I think is easy to get.
but look at those heuristics, there is not so much difference between the RT and SIR.
Exactly, that's what I'm saying.
The SIR requires a lot more
Yeah,
effort.
that's exactly what I'm saying.
One of the interesting feedback we got for Discord was on why would you want to do something like this? As a Bluetooth guy standing over there, why would I compromise? And people were interested in schemes where anything other than standard tells you to do so. What are the other monetary or credit-based schemes that would create some sort of incentive for you to do these kind of stuff? People were also interested in those things.
But I think the way we do this is sort of providing guidelines for how you should be designing things in the next generation. I don't think you're using Bluetooth and Wi-Fi now because that's what we have to play with. But if somebody had to think about this, say 10 years from now, right, how would you go about sort of engineering a system where all these things coexist? Then you would think about all the kind of things that we do. That's sort of the point. So I don't think it's it solves anything for how life is now. Life is now based on whatever standards they are, and nobody cares about what anybody else does.
So I think the integrated and example of a system where there is no monitoring something, but there's deployments and issues are accepted those protocols. We don't go in and hack or anything aggressive. Here what we haven't yet answered is in cases where Bluetooth is not critical, probably still want to keep the minimum level, so that is partly considered. But the retail guys have been asking how do I assure viewers of each stream, and to some extent. But I think our underlying assumption is that Bluetooth is a little more elastic. So what service runs on Bluetooth at 1 minute?
The voice, audio stream. I mean, not online, for 512.
So 512 I guess.
And you have the option to run your plan.
So CD, or CD quality audio
It's 350 K.
320 is what I saw on CD.
and is that elastic in most
I mean, there are different stacks for that Bluetooth audio. Some of them are like CBR kind, you have to adhere to the rate. Some of them are good with lower tempo code. But nothing for 2 Mbps except for file transfer.
When you said distributed, the CSCC is, I have to get how it is distributed. It's running on each of the.
Yeah, each radio separately decides based on the information that it has. So there's no centralized person who's saying
Okay, it just exchanges information and based on that
information at each receiver.
you keep a table of
Yeah.
CSCC things you hear and then
So again, the scalability issues now coming.
so I don't think as much because if you say CSCC range is like twice that of the larger single number.
So there's a bound on number.
But you have to keep the overhead down because the overhead is going to be packet level if you lower one. So we can't, I mean, you could do time scheduling if you were to send morning. You can do real-time scheduling, but there's no attempt. But that's why the overhead will grow as
And each node has multiple radios to go faster. Order of.
it won't go because each node is transmitting.
So the CSCC is only node specific on not radios.
So, but
Because node can snap it.
But you know that there's a company called Menu which is now doing multiple AP, intense AP and they're doing time scheduling. So that requires again some fairly tight coordination. And you have to overhead. That is that can go over the wire. But there's no attempt. I think we shouldn't rule out time scheduling gains